So yeah, so we're going to keep on with first order methods and convexity. So if you remember from last time, we were talking about gradient descent. So here, this was the contour plot of a very highly complicated function in 2D. And the blue dots are samples that we hit during the gradient descent algorithm. The blue arrows, these ones, these things right here, those are the gradients. Note that they're orthogonal to the contours, meaning that anything sort of in anything on that half space, the function is going down. And so since we follow the negative gradient, gradient descent is a descent method, hence the name. Good thing that it is a descent method, since people call it that. And we take some step size, we get to a new point here, we measure the gradient there, go along the negative gradient for some step size, and we keep on going. Most likely we get to a local optimum. If we're lucky, we get to a global optimum. Right? So, if we run gradient descent, we can, we have a bunch of choices, right? We talked about these choices. Where do we start? When do we stop? And what is our step size sequence? Where do we start? I don't have any good advice for. When do we stop was what we were talking about when the last class ended. So the first method that we talked about was the holdout set method, right? So if you're doing one of these statistical problems where the thing that you're minimizing is the expectation over some distribution of some set of functions sampled at points I and evaluated at your thing that you're trying to optimize x, then we had this sort of holdout plot where the error on your training set would keep going down and the error on your holdout set would curve back up, and you stop when it starts to curve back up, right? So that was the holdout method, and that's great if you can do it. If you can't do it, there are sort of general purpose methods for trying to figure out when to stop. And one of the best of those is using a convergence bound. So the typical convergence bounds, we were just going over this when the bell rang at the end of last class. The typical form of a convergence bound is going to be, well, there's some constant at the front that depends on the class of function you're trying to minimize, like smooth or smoothly differentiable or derivative bounds, that sort of thing. Then there's going to depend on how far away from the optimum you start. So this is the objective value measured at the initial point x0 and the objective value measured at the optimal point x star. If there's a big difference, it'll take a longer time to converge. And then epsilon is our accuracy requirement, right? So if we want a tiny accuracy, epsilon will be really, really small. 1 over epsilon will be really, really big. And so we'll have to multiply by some function of 1 over epsilon, right? And so the convergence bound recipe for stopping is you just evaluate this convergence bound, and you use it to figure out how many iterations you need to run, right? Now, in order to do that, we need to have estimates of all of these terms. We know the epsilon that we want. We can measure f of x0, but we don't know kf or f of x star, right? So we can get estimates of those usually. So we'll show you how to get estimates, lower bounds on f of x star from duality later in the class. That's not going to be what we're talking about this period. But this period, we're going to talk about what different types of function classes mean for what convergence bounds we're going to get. And that'll affect both this constant here and this function of 1 over epsilon that we're able to use. And so once we have those things, we can evaluate the bound and figure out when to stop. All right, so that's the end of the review of gradient descent. So any questions on that or from any of last class? Does anybody still remember last class? All right, so gradient descent is perfectly clear. So now this is a good excuse for us to talk about important properties that this function f that we're trying to minimize could have. And the single most important property is going to be convexity, right? So you probably have seen this definition earlier, but the definition is if you take 2 points, x and y, in our convex set C, right, and you take some real number t, which is in the interval 0, 1, right? So that means that you're drawing a line between x and y, and taking some point along that line, right? So this is tx plus 1 minus ty, right? And what you want is for that to be in C if, we'll do it in only the one direction. We want that to be implied by x and y being in C and t being in 0, 1, right? So if any time I take 2 points in the set, draw a line between them and pick a point on the line, I get another point in the set, then the set is convex. That's the definition of convexity. Now there is a maybe slightly more useful definition of convexity, which is that if I have some distribution, let's write it down here. Oh, cool. Let's take a quick break. So let's get back to, I'll see if the sound from my computer is good enough to fill in from that beginning part of the talk. So, if we have some distribution, right, which is a probability distribution P of x, right, and it's a distribution which is over the convex set C, then the expected value when x is sampled from P of x is in C, right? So this is the generalization of the line condition to more than 2 points, right? If I take any set of points and any set of convex weights on those points and take the average according to that convex set of weights, that point's also in the set. By contrast, if I take a point x here and a point y here in this non-convex set and draw the line in between, that one is not in the set, and therefore this is not a convex set. All right? So any questions on the definition of convexity? All right. So let's do some examples. So how many people can think of some good examples of convex sets? Yes? A single point, right. That's a very nice set. Any other nice trivial examples? Yeah, I think an empty set. That's sort of, some people define empty sets to be convex, some not. But yeah, let's say the empty set is convex because it satisfies that definition from the last slide, right? For all x and y in the empty set, something holds. How about all of Rn? Is that convex? Yeah, okay, cool. How about just like a line segment in Rn? Yes? Cool. How about a cube? Yes? Good. How about a star shape? No. Okay, good. There's my, looks like some cartoon character I've seen. Okay, so that's good enough. So these guys are over here, yes. These guys are over here, no. There's one that I want to mention in particular, which is if you define the p norm of x to be, you take the sum over all I of the absolute value of the ith coordinate x raised to the pth power, and then you take the pth root of that sum, right? That's called the LP norm. And if this is, if we have, well, let's write it like this. If we have the p norm of x is less than or equal to 1, where p is bigger than or equal to 1, that's convex, right? So it includes the Euclidean norm as a special case. That's when p is 2. It includes the 1 norm, the sum of absolute values, when p is equal to 1. If LP for p is strictly less than 1, that'll give you something that looks like a curvy diamond, like that. And so that won't be convex. So the p-norm is a good example of a, like p-norm balls are a good example of both convex and non-convex sets, depending on whether we take p bigger or smaller than 1. Okay. So boundaries are an interesting case. I'm going to mention them mostly so that I can phrase how I'm going to ignore them, but it's useful to know about these things. So X is on the boundary of a set, which is written this sort of weird delta times weird delta C. That means that no matter how small a norm ball you take around X, not all of that norm ball is in is part of that norm ball is in C and part of it is outside, right? So if I take so I'll just write BP of X comma epsilon. That's the set of Y such that the P norm of X minus Y is that's the P norm is less than or equal to epsilon, right? Actually, let's take an open ball. So I'll just do that, right? And if I if BP of X comma epsilon intersect C is not empty, and BP of X epsilon intersect C complement is also not empty. X is in the interior of C if the opposite holds. BP of X epsilon is contained in C for small enough epsilon, right? So here I have a nice convex set. This is the 2 norm ball, right? I'll take a point which is on what we think of as the boundary, right? And I'll draw a norm ball around it. And that's part way in, part way out, whereas if I'm here, I can draw a norm ball that's entirely inside, right? The relative interior means that we take the smallest subspace, we'll call it S, which contains C, right? And then restrict to X, restrict to S, right? So throw away all of Rn outside of that subspace, and then ask, are we in interior? In the interior of C, restrict to S. I don't want to write a formal notation for what C restricted to S is, but you get the idea, right? So yeah, so boundary interior and relative interior are important for being able to define open and closed, right? So we're going to say that C is closed if the boundary of C is contained in C, right? And it's open if the boundary of C intersect C is the empty set, right? So you can have sets which are neither open or closed, right? A good example of a closed set is this ball right here, right? Because it contains all of its boundary points. If we changed it to less than 1 as opposed to less than or equal to 1, it would be open. And then if we included sort of, let's say, this half of the points on the boundary, it would be neither open nor closed. All right? So questions about boundary open or closed? All right, looks like this is maybe review from, oh, yeah. Oh, you can fix P. Whoops. So let's just take let's say take P equals 2 below. They should be the same in any finite dimensional space, no matter what P bigger than 1 you take. So if I take a look at this set right here, this is the probability simplex in 2 dimensions, right? So this notation, this means that x1 is bigger than or equal to 0 and x2 is bigger than or equal to 0, right? So I'm inequality on a vector I'm taking to be component-wise. So the probability simplex is every component is bigger than or equal to 0, and the sum of all components is 1, right? So this set, its interior is, well, so what is the interior of this set? Anybody want to guess? Empty, yeah, right. Because if you think of any ball, right, around any one of these points, it's not contained within this set. But if we restrict to this subspace, the subspace where things sum to 1, then the interior is going to wind up being everything from, well, it's going to wind up being everything except for, like, make an open point at both ends of it, right? So that's the difference between interior and relative interior. Yeah. So the question is, what is the case where you would use a relative interior? Often you might want to talk about a set without specifying what the containing space is, right? And then you would talk about the relative interior, right? You might want to be agnostic about whether this simplex set is embedded in R1 or R2 or R7, in which case the relative interior is the same for all of those embeddings, but the interior depends on the ambient dimension. All right. Were there any more questions? Yeah.
Sorry, one more question about the same thing. But can ever the relative interior be different from interior plus boundary? Because in all your examples, it's just interior plus boundary.
Oh no, it's different here, right? So the boundary, these 2 endpoints here are part of the boundary in R2, but the entire thing is part of the boundary in R2, right? And so when we go and embed it in R1, these 2 points stay on the boundary, whereas the rest of it becomes relative interior. All right. All right. Here's another interesting case. What about all of Rn? Is it open or closed? Take a vote. How many people think it's open? Okay. How many people think it's closed? All right. It's a trick question. It's both. Right? Because its boundary is empty, and therefore it contains its boundary, and also the intersection with the boundary is empty. Right? So it's both open and closed. So that's a nice. That's actually useful, right? Because when you wind up stating things that apply to all open sets or all closed sets, both of those wind up applying to all of Rn. Right? How about an empty set? Any guesses for that one? We'll take a vote. Open. How about closed? Good. Same hand stayed up. It's both. Right? So you're not going to be fooled twice. At least not by the exact same trick. And then the final thing that I want to mention is compact, which for our purposes is the same as both closed and bounded. Bounded means it's contained within some ball centered at the origin. Right? For those of you who know some topology, there's a more general definition, which is every open cover has a finite subcover. For all of the spaces we're going to be dealing with, the 2 definitions pick out the same sets, but there are sort of other topological spaces where they're not the same. We don't need to worry about that. So compact is closed and bounded for our purposes. Okay. All right, so One good way to get convex sets is convex hull. So what a convex hull is, it's it's basically all of the points you can get by taking convex combinations of the points in the set. So it is the set sum over I of AI xi, where xi is in your set C, and all of the AI are greater than or equal to 0, and the sum of the AI is equal to 1. Right? So what that means here, right, is, well, so I can take these 3 points as being AIs, so I can fill in this entire triangle, right? I can take these ones, I can fill in that triangle, right? And so just if you think about it, I wind up getting everything that's inside this set of this figure here, right? So it'll be all of these guys here, right? So in some sense, it's the smallest convex set that can be that contains the points that we're interested in. And it turns out that any closed convex set C is equal to the convex hull of some points x, right? So I can take a set of points x, and C will be equal to the convex hull. It's possible that the size of x is infinite. I might have to take infinitely many points. So if you think about, for example, a disk, right? I can represent that as a whole bunch of n-gons as n is getting higher and higher, right? And so it's the limit as the number of points in the sets goes to infinity of the convex hull of the corners of an n-gon. Okay? All right. So I can also take any convex set. Well, I can represent it as, so not any convex set, but I can take I can take convex sets and I can draw a hyperplane like this, right, and take everything on that side. I can draw another hyperplane like that, take everything on that side, right? Another hyperplane like that, take everything on that side, right? And I think I have 1 and 2 more. Right? And so this convex set is the intersection of a whole bunch of half spaces, right? So I can take, in this case, C is equal to the intersection of over the coefficients of the half spaces AI and BI of the sets X such that AI X plus BI is less than or equal to 0, right? And again, any closed convex C equals this, right? So I can represent it as the intersection of some number of half spaces, possibly infinitely many, right? So for example, the circle example again, I can take one half space that's tangent to the circle at each point on the border. That's infinitely many of them, but the circle is equal to their intersection. Yeah. You can right. You can do it with only countably infinitely many. All right. So these are called the primal and the dual descriptions of a convex set. This is the first example, I guess, that we've hit of duality. You guys are going to be very tired of me saying the word dual by the end of this course. But it's a nice, yeah. They're two different representations of the same thing, and sometimes one of them is easier to work with and sometimes other. And that's essentially what the word dual means. Two different representations of the same thing, which are different enough that they're not obviously the same, and sometimes one's easier to work with and sometimes the other. All right. So some properties of convex sets. One important one is the supporting hyperplane theorem. So for any point that is on the boundary of a convex set C, right? So I'll take on my point x0 to be there. I can draw a hyperplane such that it goes through x0 and the entire convex set is on one side of it, right? So what that means is that x0 dot w is equal to b, right? And x dot w is less than or equal to b for all x in C. Okay? Maybe geometrically kind of obvious, but it's nice to know that it's a theorem. Anytime I find a point on the boundary of the set, I can draw a supporting hyperplane through it. Now, sometimes the supporting hyperplanes can get tricky. So here are a couple of examples. Suppose I take my set to be x squared plus y squared is less than 1, right? So that is the open disk, right? So it's everything inside but none of the outside. So the supporting hyperplane theorem is true for this set, but it's true in kind of an annoying sense. There are no points on the boundary, therefore there don't have to be any supporting hyperplanes, right? But it's true, so that's always nice. Maybe a more interesting example is the L1 norm. So suppose I take the absolute value of x plus the absolute value of y is less than or equal to 1, right? Less than or equal to this time. So that's a diamond like this, right? So if I take a point x0 here, the supporting hyperplane is nice and obvious, right? It's like that. But suppose I take this point here, right? So there's a supporting hyperplane like this, and there's another supporting hyperplane like this, and in fact there are infinitely many supporting hyperplanes at that particular point, right? So the supporting hyperplane isn't unique, but there always is one at every boundary point. Okay. So another good property is the separating hyperplane theorem. So two convex sets, C and D. So here's one convex set C, and then D is going to be just this point here. And what we want is for C not to intersect D. So C intersect D is the null set. Then there's going to be a hyperplane that goes between them, right? So what that means is w dot x is less than or equal to b for x in C, and w dot x is bigger than or equal to b for x in D, right? And if both C and D are closed sets, and at least one of them is compact, you can get stronger. You can make the inequalities strict, right? So for example, w dot x is less than b, or w dot x is greater than b, right? And so in this case, these guys are both closed and both compact, and so there is a strict separating hyperplane. But in general, the separating hyperplane might not be strict. Okay? Can anybody think of an example where the separating hyperplane is not strict? Right. So just to repeat that, if you have an open set and a point on the boundary of that set, right? So if you have, I'll draw my beautifully rendered open disk here, right? And here's a point that is on the boundary, and there is a separating hyperplane, right? But it is not strict separating hyperplane. So it turns out that you can get a lot fancier than that. Anybody happen to be able to think of another example that doesn't fit this mold? Yeah. The complement isn't convex. So you're right, there's no supporting hyperplane, but it's for a different reason. The complement isn't convex. Yeah. A half space and its complement. Yep, right. So a half space and its complement. I don't know how to draw that, so I'll just say half space and its complement. All right. So I was thinking of an even trickier example. If I take the set y is greater than or equal to 1 over x, right? So that looks like this, right? And then the set y is less than or equal to 0, right? Which looks like this. Both of these sets are closed, but there's no strict separating hyperplane, right? So the only separating hyperplane is the horizontal axis, right? One of the sets is always above it, the other is always below it, but both sets come arbitrarily close to touching it, even though they never intersect. Right? So I always like that example because it's you don't think of it. You don't think of an example like that to start out with, but it's always a nice one to have in mind because it winds up breaking a lot of things. And the reason the strict version of the separating hyperplane theorem doesn't hold is that neither one of these sets is compact, right? They are both unbounded sets, even though they're both closed. Yeah.
So if you're in R1,
Yep.
and you take the closed interval 0, 1,
Mm-hmm.
and then the negatives, 0, 1 is compact. It's not strict separate.
Right. Both sets have to be closed, right? So if both C and D are closed,
Oh, okay.
and at least one is compact. So so the example was, let's say in R1, the x greater than or equal to 0 and its complement x less than 0, right? X 0 is equal to the closed interval 0, 1 and x less than 0, strictly less. At least one is compact, but both of them are not closed, right? All right. So you might, at some point, be required to prove a set convex. Not saying, just, you might. There is a homework coming up. So there are a few ways to do that. Using the definition directly is perhaps the simplest one, right? So you just write down tx plus 1 minus ty, and you prove that that's in C, given the assumption that x and y are both in C. You can use the primal or the dual representations, right? So you can represent it as a convex hull of some set of points or an intersection of some set of half spaces. So either one of those representations might be easier to work with than the direct definition. There's also a partial converse to the supporting hyperplane theorem. So if your set C is closed and has a non-empty interior and has a supporting hyperplane at all boundary points, then it's convex, right? So the supporting hyperplane theorem says that if C is convex, then every boundary point has a supporting hyperplane, and the closed and non-empty interior don't come into it, right? So it's this is a partial converse of the supporting hyperplane theorem, and it's sometimes useful for proving convexity. This, by the way, is mentioned in the Boyd and Vandenberg text if you want to get some more detail on it. But the way that's actually by far the most common is to take our set C and build it up from simpler sets by using operations that preserve convexity, right? So you take convex sets and you munge them together somehow using operations that preserve convexity, and then the result winds up being convex. So what are these convexity-preserving operations? Again, there's a complete list in Boyd and Vandenberg, but I wanted to list some of the most important, right? So translation, x plus b for x in C, right? So this we'll call C plus b is equal to that. So b is just some vector, and you shift the set around by that vector. Scaling, right? So we have lambda x for x in C and lambda greater than or equal to 0. Right? I guess I should put this here. We're fixing lambda greater than or equal to 0, and then we're multiplying every point in C by lambda, and so we're calling that lambda times C. That's going to wind up being convex. An affine function, right? So ax plus b for x in C, right? And this is for some fixed a and b, so we'll call it a times c plus b, right? And an interesting special case of this is projection. So an example of a projection operator is you just drop some coordinates from your set, right? So if you think about, for example, you have a circle and you project it onto the line, right, like that. You wind up getting this interval here, and that's a convex set. And you can see that that's an affine function because the function is just the identity for the coordinates you preserve, and it does nothing else. It does nothing. There is no output for the other coordinates. Intersection, right? So C intersect D, where both C and D are convex, is a good example. Set sum, so we'll call that C plus D. That's x plus y, where x is in C and y is in D, right? So this is every way of choosing a point in one set and every way of choosing a point in the other, and then you add all of those together, right? So for example, if I take this circle and add it to an interval, I'll get this thing that looks like a circle moved through an interval, right? So looks kind of like, I don't know, like a capsule, a pill capsule or something, right? So that's an example of set sum. And then the one that nobody ever seems to remember is the perspective function, which is, it's actually turns out to be pretty useful, but it's kind of weird to describe. The intuitive way of thinking about it is that you have some set, convex set, and you stand back and view it through a pinhole camera, right? So you can see here's my convex cube right here, and it's somewhat distorted because the things farther away are smaller and the things closer are less small. And then you project it onto the image plane, right? So the image of this cube will wind up being this sort of six-sided figure here, right? And it's not quite a regular hexagon because of the distortion introduced by the projection operation, right? And it includes everything, every point in the cube that would project onto there, right? So if you want to write that in 3D, you would have for x, y, and z in C, you would have x over z and y over z, right? So you'd lose a dimension, divide each of the first two by the last, and you have to restrict that z is always greater than 0 whenever you're in C. Okay? Yeah? You can scale something all the way down to 0. You get just the origin if you do that. The question was, do you need lambda bigger than 0 for the scaling operator? And the answer is, it's OK to scale a set by 0, and you just get only the origin as long as C had at least one point in it. Other questions? Yeah? No, you can just combine scaling with an affine function, right? So you negate the set and then scale it. Yeah, so matter of fact, I'll just go and drop that. Because it'll work just fine with a negative one. All right. So here's a nice example of a convex set. So recall that the matrix A being bigger than or equal to 0 with this funny little curly greater than or equal to sign. That's a notation for being positive semi-definite. And it means that x transpose AX is bigger than or equal to 0 for all x, right? And so if we have the symmetric positive semi-definite matrices, we can prove that that's convex in two ways. One is that I can just directly use the definition of convexity, right, and expand that to x transpose AX times T plus 1 minus T times x transpose BX. And if this is bigger than 0 and this is bigger than 0, well, their average is bigger than 0, right? So that's a very nice, simple proof that the set of positive semi-definite matrices is convex. The other, which I think is perhaps even cooler, is I'm going to rewrite x transpose AX. So if I write out the matrix multiplications, this is the sum over all coordinates I, sum over all coordinates j, of xi times aij times xj, right? And if you look at this, this is a linear function of a for a fixed x, right? It's not a linear function of x, but it is a linear function of a. And so saying that that's bigger than or equal to 0, right? That's a half-space constraint. There's one such half-space constraint for every x. So now I'm intersecting uncountably many, in this case, half-space constraints. And so the result, since each of the half-spaces is convex, is a convex set, right? So this is, to me, it's a much cooler proof, even if this one's simpler, right? The second one blows your mind. The first one makes you like, oh, well, you didn't meet the second one. All right? So any questions about any of these?
Why did you say there are uncountably many half-space?
There's one for every possible x, right? So for every vector x in Rn, you get a constraint that looks like that one there. And you intersect all of them. You could actually just intersect them for a dense subset of Rn if you wanted to. You could get countably many. But it's easiest to see if you just intersect all uncountably many of them. So another example that's maybe more related to machine learning and statistics is suppose that I have a convex set of distributions, right? So I have a vector x with, let's say, 7 components, right? So x is in, it's a binary vector, so each component is 0, 1, and then there are 7 components, right? And so a probability distribution, I can think of that as a vector with 2 to the 7 elements in it. And I can ask for a convex set of probability distributions in the sense that if I average any 2 of those distributions, I get something in the set. And then I can ask for the set, the conditional probability of x1 through 5 given x, 6, and 7, right? So by Bayes' rule, this is just the probability of x1 to 5 divided by the probability of x, 6, 7, right? 1 to 7? No. Probability of x. So the conditional probability of x1 to 5, right? That's a, I take the probability of that x1 to 5, right? And this I can represent as a sum over all possible values of x, 6, and 7 of the probability of x1 to 5 and x, 6, 7, right? So it's a marginal of the probability distribution. So I take the marginal onto the first 5 components, and I divide it by the probability of, oh, you're right. This is what comes from writing my slides too late at night. So we'll just erase that, pretend it never happened, except for the video that's going to be on the internet. Right. Probability of x 1 through 7 divided by probability of x 6 and 7. Right, and so I'm thinking of this now as a vector with 5 components. I'm getting the conditional probability distribution over x1 through 5 for a particular fixed value of x, 6, and 7, right? And so the numerator and denominator are both affine functions of a convex set, so they're both convex. And so I can think of this as a perspective function, right? So I make a, I just divide a component of, divide some component of a convex set by the remaining last component, and then drop that last component. Okay? So this is a use of the perspective function. Today is a day of technical difficulties, it sounds like. Apologize for the brief interruption. All right. So right. So this is the it is yes convex because of the perspective trick that I mentioned. Yeah.
It's also possible to do it directly as a projection.
So how do you get the norm? So the question is, can we view it as just a projection? And the question is, how do we get the normalization operator, the normalization constant, if it's a...
It's possible to find
So are you thinking a perspective projection, or are you thinking an ordinary
orthogonal.
orthogonal projection? We'll have to discuss that maybe after class. I don't see it at the moment, but we can discuss it after class. All right. So, oh, there's a question over there. You have to speak up a lot louder. So it's a set of distributions that's convex, and so I'm considering each distribution as a vector where I take the probability of every atomic event and concatenate them all into a vector. And then I can have a set of such vectors, and that set can be convex in the sense of r to the however many atoms there are. All right. So the epigraph of a function so what I'm going to do now is connect convex sets to convex functions. The epigraph of a function is defined to be, so we have some function f, right? And the epigraph is defined to be all of the sets x comma t, all of the points x comma t such that t is greater than or equal to f of x, right? So here, the epigraph of this function, it's just all of this area inside this nice camel hump, upside down camel hump sort of curve, right? So it's a pretty simple definition. What is the epigraph good for? Well, actually, one thing first. So the domain of a function is defined to be all points x such that f of x exists, and also f of x is finite, strictly less than infinity. Okay? So for example, the domain of the function 1 over x, right, is not all of r, right? 1 over r. Oh, r minus 0, right. So r minus the origin. The domain of log x, at least assuming we're doing the real valued version of log x, right, that's x strictly greater than 0, right? And so now a function is convex if and only if the epigraph is convex, right? So f convex as a function is the same as saying that the epigraph of f is convex as a set, right? So both of these sets here are convex. Both of these functions here are convex, right? So I take this epigraph here, that's a convex set, and this epigraph here, that's a convex set. And that's equivalent to saying that the domain of f is convex, and we have something that looks like the set convexity condition that t times f of x plus 1 minus t times f of y is greater than or equal to f of tx plus 1 minus ty. And that has to be true for all x and y in the domain of f. Right? So first, the domain itself has to be a convex set, and second, this condition has to hold for all x and y in the domain. A lot of times people forget to check the condition that the domain is convex, so you always have to check that as And there's also, you remember there was an expectation version. So for any probability distribution P of x over the, for x in the domain of f, right? We have that the expected value when x is sampled according to P of f of x has to be bigger than or equal to f applied to the expected value when x is, right, the expected value of x. Right? And that's just the generalization of the two-point condition to the many-point convexity condition. All right? So convex sets and convex functions are pretty clearly very strongly related. And the relation goes through this idea called the epigraph. Okay? So there's another interesting relationship between convex sets and functions. If we have a function that's convex and we take what's called a sublevel set, x less than or equal to some value k, this is called a sublevel set, right? Then the sublevel set of a convex function is convex, right? So if we take the 1.5 sublevel set of the this absolute value function, right? It's going to wind up being this interval here, and that's convex, right? And the reason that that's true, well, you take the epigraph, you intersect it with the constraint that it has to be less than or equal to k, and then you take the projection onto the x-axis, right? So it's a good example of using the convexity preserving operations to show that a function, to show that a set is convex. Yes, I do in fact want to say f of x. Thank you. All right, so here's an interesting conundrum. Is there a converse to this? If all of the sublevel sets of a function are convex, is the function going to be convex? Put it to a vote. How many people think yes? And how many people think no? The no seems to be winning. Somebody who said no, can you give a counter example? Okay, so somebody went like this in the back. I don't think the camera picked you up, but yeah. So for example, if we take f of x is equal to the square root of the absolute value of x, right? So that's the seagull function, I guess, that was being indicated, right? And all of the sublevel sets of that are going to be convex, right? But the function itself is not. And in fact, this is an important enough concept that it has a name. Functions, all of whose sublevel sets are convex, are called quasi-convex. Okay. And some of the algorithms that we're going to talk about work even for quasi-convex functions instead of convex ones. All right. Quasi-convex functions are not convex, but they share some of the properties of convex functions. All right. Yeah? And functions with what? Right, so quasi-convex functions will have a unique global minimum, but not every function with a unique global minimum will have convex sublevel sets. Right, so for example, take the LP norm for p equals a half. Right, the sublevel sets are these sort of curvy diamond shapes that I mentioned before, and yet it has a unique global minimum at the origin. So geometric questions like this are really good ones to ask, right? Thinking of examples and counterexamples is the only way to get intuition for convex sets. All right, so you might be asked at some point to prove that a function is convex. If you were going to do that, you could use the definition directly, right? Look at the epigraph and show that it's convex, or use the definition, right? F of tx plus 1 minus ty has to be less than or equal to tf of x plus 1 minus tf of y. Yeah. The constant function, sorry, you're right. So what I said was too strong. The global minimum is not unique. There's a convex set of global minima. Thank you for catching that. Right? And the counterexample is the constant function, right? There's not a unique global minimum, but it is both convex and quasi-convex, and it has a convex set of global minima, namely everything. So, right. So you can use the definition directly. You can reduce it to the problem of proving that the epigraph is convex. For example, if you tried to use supporting hyperplanes to prove that the epigraph was convex, what you would get is exactly this, right? You would get that f of x is bigger than or equal to the supporting hyperplane at y. How do we get a supporting hyperplane at y for a function? Well, it's going to be like this, right? So first order Taylor expansion. So it'll be f of y plus x minus y times f prime of y, right? So if we showed that, right, and if we showed that for every x and y, well, that's the supporting hyperplanes at every boundary point of the epigraph. And so if it has that supporting hyperplane at every boundary point and the other conditions of the partial converse are true, then you get convexity, right? But this particular example is important enough that people write it actually sometimes as the definition of a convex function. And it's called the first order convexity condition for a function. You might guess from the fact that there's a first order that there's also a second order convexity condition. And that second order convexity condition is this. If we take the second partial derivative of f evaluated at some point x, that has to be always greater than or equal to 0. Right? So if you think of a parabola, right, that has a constant positive second derivative. And so that's a good example of a convex function. Okay. And then, of course, one of the most common ways to do it is to construct it at the end from a whole bunch of simpler convex functions using convexity-preserving operations. So let's take a look at the convexity-preserving function operations. We could have non-negative weighted sum, right? So, for example, AF plus BG, well, that's equal to, let's write it. So the function AF plus BG at x is equal to A times f of x plus b times g of x, right? And so if a and b are both non-negative and f and g are both convex, then AF plus BG is convex. The pointwise maximum, right? So g of x is equal to the supremum over I in some set I of fi of x, right? So, for example, if you take the larger of the absolute value and x squared, right, you'll get something that looks like a point at the origin, and then at some point it starts becoming a quadratic, and that's going to be a convex function. You can compose it with an affine function, right? So f of ax plus b is going to be convex if f is convex. This one's kind of weird. If you have a monotone convex function g, right? So g monotone, meaning that it just keeps increasing or staying the same as its argument increases, and it's also convex. Then g of f of x is going to wind up being convex. That's maybe, I don't have a good intuition for that, but it's sometimes a useful thing, right? So for example, if I take 1 over x, right, or I guess 1 over minus x, that'll be monotone increasing and convex, and I can compose that with a convex function, and it'll be also convex. There's a perspective operation for functions as well, which you can think of as being like doing the perspective on the epigraph. So what that's going to be is that g of x comma t is equal to f of x over t times t, right? Where t has to be bigger than 0. So again, just like perspective for sets, that's maybe kind of a counterintuitive notion, but you can show that that preserves convexity. And then finally, if we have some function f and y, f of xy, that's jointly convex in xy together, and we have some convex set C, we can define another function g of y by taking a particular x, or sorry, a particular y, and minimizing over all x and c, right? So that function, let's assume that that minimum is always bounded below. In other words, it's not minus infinity. This function is going to wind up being convex if f was convex. And the intuition for this is kind of cool. If you take the epigraph of f, right? So epi f is equal to the x, y, and t, where t is bigger than or equal to f of x, y, right? And now if we look at the epigraph of g, right, we can get that by just dropping y from the epigraph of x, right? Because the minimum, if I have some y where f of xy is bigger than or equal to t, well then g of xy is also going to, where t is bigger than or equal to f of xy, well g, because I get to minimize over y, let me start again. I drop the x from the epigraph of f. And so if I have some point xyt, which is in the epigraph of f, right, that means that f of xy is less than or equal to t. That means that g of y is going to be less than or equal to t as well, because I could always pick this x, right? And so epigraph of g is a projection of the epigraph of this other one, and therefore the epigraph is convex, and therefore g is convex. So that's kind of a cool argument as well. All right. So maybe a much simpler example is the absolute value function, right? So maybe I should have done this one first as a warm-up, but we know that the absolute value of x is bigger than or equal to x. We also know that the absolute value of x is bigger than or equal to minus x. So if I take the absolute value of tx plus 1 minus ty, well, let's do a case analysis, right? So suppose that tx plus 1 minus ty is bigger than or equal to 0. So that's an if, right? Then the absolute value of tx plus 1 minus ty, that's equal to tx plus 1 minus ty, right? And that is less than or equal to t times the absolute value of x plus 1 minus t times the absolute value of y, using these inequalities here, right? And then the otherwise, right, if this is smaller than 0, well then tx plus 1 minus ty, that's equal to minus tx minus 1 minus ty, right? And here now, using the negative x and the negative y, this is going to be less than or equal to t times the absolute value of x plus 1 minus t times the absolute value of y, right? So this is a nice, simple example of how you would prove that a function is convex. Yeah? Yes, that's right. So generally, there's always going to be more than one strategy for proving a given thing convex. The strategy of of examining the epigraph of this function and proving that it's convex because it's the intersection of two half spaces. That's a nice simple way to do it as well. And maybe it gives more geometric intuition than the way that I gave right here. Okay, so if we have a function in more than one dimension, right? All of these above methods still work, except that I have to write the second order condition a little bit differently, right? So I'll say h is equal to the matrix of partial derivatives, d squared by dx squared f of x, right? And so, for example, in 2 dimensions, it would be something like d squared by dx squared f, d squared by dx dy f, right? D squared by dx dy f, and the last one is d squared by dy squared f, right? So that would be the Hessian in 2 dimensions. And the condition is that the Hessian has to be positive semi-definite, right? So instead of just, this is a generalization of the condition that it has to be bigger than or equal to 0. If there's just one dimension, the Hessian's just a single number, and that number has to be positive. Yeah.
Can you talk about when this doesn't exist, like when it's a non-single function?
If it doesn't exist, it's difficult to apply the second order convexity condition. Yeah, I mean, you can, often in that case, you could split the function into 2 pieces, prove one of them convex by the second order and the other convex by another meaning, right? So if you know where the discontinuities are, you can split them apart that way. But yeah, you could also, for example, lower bound the function by a parabola at every point, right? And then its epigraph would be the intersection of all of those parabolas. Right, so you could do that even if the function was not. So that would be that's probably the best generalization of the second order convexity condition. Okay. And one way to check this is you pass h to the eig function in MATLAB and check that all of the eigenvalues are real and positive. Of course, you can't use that in a proof because you can't say, okay, MATLAB, check the Hessian at every real input. But that's basically what the condition means. Right? The other thing that's kind of interesting is a reduction to 1 dimension. So if I take my multidimensional function and I take some line, x0 plus t times d, where d is a direction, t is any real number, and x0 is a point, right? So what that means is something like x0, here's d, and then x0 plus t times d is, well, it keeps going off the slide, but you get the idea, right? And if for every x0 and d, we have the function f of x0 plus td is convex as a 1-dimensional function, then f itself is convex. Right? So in multiple dimensions, you get some additional flexibility. And also some additional difficulty, but they trade off against one another. So any questions so far? Yeah.
What about the first order condition?
The first order condition still works, right? So it's going to wind up being something like f of x is greater than or equal to f of y plus x minus y, and now it's a dot product with the gradient of f at x. Right? So it's the same thing. I could even have written, df dx so that the notation was the same. Yeah. Hmm? No, I think it is not true. Right. You can compose with an affine function on the interior of f, or as long as the multiplier is non-negative, you can compose on the outside of F, right? And so people think of those as separate cases because you have to impose a condition on one that you don't on the other. But for the monotone one, you can only have G on the outside of F, not on the inside. G being the monotone convex function, yeah. All right. So, any other questions? Is that a question? Louder?
Gradient f at y or
Oh, at, sorry, gradient f at y. Thank you. It's nice that you can just erase things without them ever having been there. All right, so I wanted to do a more complicated example. I don't think we necessarily have time before the end of the period, but I want to at least set it up. So suppose that I'm trying to do handwriting recognition, right? So I have some nice randomly chosen word like convex here, right? And so I got that by writing, on my tablet these letters, and I can split it up into individual letters like this, right? So I put a box around each of them, and I can try then to do handwriting recognition, which means selecting for each one of the letters which of the 26 possible lowercase letters is it, or maybe which of the characters that I can type on a standard keyboard, about 100 of them, is it, right? And so so here, right, what I'm going to do is say that xi is going to be the pixels of character I. Yi is going to be the label, right? So A through Z. And in order to make a classifier, I'm going to design some features, right? So the features of xi could be something like, well, I'll pick some region of the image, right, and ask how much total ink is within that region, right? Or I could run an edge detector over the image and ask how many edges or how much edge weight is within that or how much corner weight is within that region, right? So that's the sort of thing that I'm thinking of for image features, right? So this is a feature of a character. Then from those features, I'm going to define a whole bunch more features. So I'll write phi j of xi, right? And then I'll multiply that by an indicator, a Kronecker delta, of whether yi is equal to k, right? So an example of this would be the amount of ink that's within some region if the character is an n and 0 otherwise, right? And so what these are going to do, they're going to let me represent correlations between the features and the labels of each one of the characters, right? And then yet another set of features, chi ikl, that's going to be just an indicator of whether yi is equal to k times the indicator of whether yi plus 1 is equal to L, right? So these are bigram features. They're basically features that say I have an N followed by an O, or a V followed by an E, right? All right, then given those features, I'm going to write a criterion function. So I'm going to define weights, which are let's say Wij as weights for these features here, and Vikl for these features here. And so I will write my criterion function as the sum over all I, j, and k of psi ijk times wij plus the sum over ikl of chi ikl of yi and yi plus 1 and then I'll multiply those by VIK alpha, right? So this is now, this criterion function, it's a linear function of the weights, right? And my classifier is just going to be, well, I'm going to say that I know V, W, and X, right? I know the images and I know all of my weights. And I'm going to say that I'll pick the Y, which is just the arg max over all possible Y of L of X, Y, V, W, right? So this is going to be a linear classifier, right? I compute a whole bunch of linear functions, one for each possible value of y, and I select the one that's highest. Okay? And now if I want to learn this classifier, well, I'm going to get everything right. I'm going to get everything right in the following circumstance, right? If L of X, Y, V, W is bigger than or equal to, well, no, I want it strictly bigger than L of X, Y prime, V, W, and that's for all Y prime not equal to Y, right? Then I'll get the classification right. And so what we want is something like this. L of X, Y, V, W is greater than or equal to the max over Y prime of L of X, Y prime, V, W plus pi of Y comma Y prime, where pi of Y, Y prime is going to be 0 if y is equal to y prime, and it will be greater than 0 if y is not equal to y prime. So for example, I could just take it to be 1 in that case, or I could take it to be the Hamming distance, right? So y and y prime are both sequences of characters, CONVEX, and so maybe CONVCX is closer than PQBDE, right? So the Hamming distance I could take as my measure of how far apart. Okay, and now this right-hand side here, right? So this is everything inside these parentheses is a linear function of V and W for a fixed y prime. I'm taking the max of a bunch of linear functions. So pointwise max of convex functions is convex. So the right-hand side is now a convex function of V and W. Okay? So I'll just write that. And now if I take the right-hand side minus the left-hand side, right? So if I take this guy and subtract it from both sides, well, this is a linear function of V and W. So right-hand side minus left-hand side is still convex. And so what's going to be true? If that right-hand side if the right-hand side is 0, then that means that everything's good, right? It means that it means that the true thing is actually strictly bigger than every other thing because I've got these pi things in there that push the y and y prime apart, right? But if the other way, right, if it's really big, right, that means that the constraint is badly violated, right? So in other words, if this is much bigger than this, then the constraint is badly violated. And so what I want to do then is to minimize over all V and W the sum over a whole bunch of training pairs T of the right-hand side above for training item T minus the left-hand side above for training item T, right? So that's a convex function because each one of its terms is convex. And it's bounded below by 0. And therefore, it's a reasonable thing to do to try and minimize it, and I just showed that this is a convex optimization problem. Right? So that was kind of fast because we were coming to the end of the class, but are there any questions on it? Yeah. Right, there's a very large number of constraints. I haven't shown how to do this efficiently. I'm just showing that it's a convex function. All right, thanks a lot, and we'll see you next time.